Hi guys, I'm glad you guys could log on. I'm going to do the lesson for 7.1, the notes that you have on area between two curves. I'm going to go over to the broadcast system, so everything I do is going to follow your notes. I do want you to fill in the notes along the way, which includes graphs, equations, antiderivatives if we do them, and clearly answers. What you're going to do is you're going to need your calculator. So we're going to be typing antiderivatives into the calculator so we can use that method of evaluating integrals, as well as, remember, we're going to be doing some by hand. Pause if you need to sketch stuff, rewind if you need to, fast forward, whatever you need. But the lesson that you have on 7.1 is going to have a component in practice that I have also assigned to you. When we get back after break, I'm assuming that 7.1 is good, we're good to go, and we can move on to other volumes from this chapter. So, on to the presentation. We have here 7.1, which is areas in the plane. In our book, it's called, I believe, area between two curves. We've talked about areas before, areas under a function to the x-axis. This is going to extend our definition of areas as defined by the definite integral into areas between curves, or above and below the x-axis. We're also going to be looking at how these two curves intersect, and we therefore enclose an area. Sometimes when we have functions that go back and forth along each other, like two polynomials or two trig functions, we might have function areas that switch in terms of different functions maintain the top of the border and other functions maintain the bottom of the border. And then normally our antiderivatives are in terms of dx. We will also do area sideways in terms of dy. So you'll see what happens there. And occasionally, area is always occasionally decided by using some geometric shape. Triangles, circles, squares, whatever we have. So let's talk about a definition first. If we have two functions that are continuous over an interval, notice this is a closed interval from a to b. That would be like, for instance, from x equals 2 to x equals 5. Then we talk about the area between the curves between f of x and g of x from a to b is the integral of f minus b, or f minus g. Now that indicates that f is on top of or over or greater than g. And so we'll have the integral of the f minus g. I like to call this top minus bottom. And this is how you'd see it in an integral. So you notice that we have the definite integral from a to b. That would be from the left to the right on the x-axis. F would be the top curve minus g, the bottom curve. And this is all in terms of dx. So we're talking about widths, little teeny widths of x. See your first example. Oh, no, we have a picture first. Okay, so in this picture we show you how if f was on top of g or always over the function g, we can see that we can draw little rectangles. Now these little teeny rectangles are measuring area, and each little teeny rectangle has a width and a height. And we go all the way from A over to B. So if we draw an infinite number of rectangles between the two curves, and remember that's starting over here at A and ending at B, we're always going to get the height of each one by subtracting the y values in order top minus bottom. Again, f minus g, and this would represent our height. And if we fill in an infinite number of rectangles, as we've talked about before with integrals, we can sum up every single rectangle all the way from the left to the right, and every rectangle is going to be defined by a height times a base. Well, the base is that little teeny piece of x, and so we've come to know that as dx. So an area equals a height times a base. And that's what you see inside of the integrand. Let's look at an example. Find the area between these two curves. This is your first example. Now, before I go into graphing this, we're going to talk about the steps for all of these we're going to either sketch or graph by hand on the calculator or by hand the two functions so that we can just identify which function is on top and which function is on bottom. We're going to find the points of intersection. Now that would be the enclosing parts between the two graphs, or we might be provided with a beginning and an ending. We're provided with a beginning and an end of an x value interval, then we don't even have to worry about this. I want to sketch a graph. We're going to be doing that quite a bit this section, and drawing in one rectangle so we can identify the height and the base. And then we're going to use the functions to interpret base times height or height times base in the integral, set up the integral, and evaluate either with an antiderivative by hand. We're going to take an antiderivative and evaluate by hand, or we might use the calculator, jumping to the calculator types of questions. So here we go. Here is the curve that we see for the two functions given. Hopefully you can identify, just because these are polynomials, which one is on top and which one is on bottom. And it looks like the upside down what is it? It's a parabola. This would be what we call the top function. And I see it's on top right here. And then the other function, y equals x squared, generates the bottom. I can look at where that top and bottom curve intersect to form a region. So the region is contained in between those 2 points. So we have to find out what those points of intersection are. Now, clearly on a calculator, you can use the functions on the calculator to calculate the intersections, but here I might have to actually solve it by hand. And if we find intersections, remember, intersections are found by setting the two functions equal to each other. So I can just do a little bit of math here, and I got, that's an equal sign. Add my negative x squared to the left-hand side, divide by 2, and so I get x intersections of positive and negative square root of 2. And that's what values are right here on the x-axis. If you're going to do this on the calculator, you're going to get a decimal. If you're going to get a decimal and you want to use the calculator, we're going to talk about that probably back when we get to class, but we can use a storing function, and we can store the left intersection as the letter A and the right intersection as the letter B. And then when I type in my integral, instead of typing in decimals and how many do I round to, I can actually get an exact number, A and B, just by retrieving them. So we'll talk about that once we get back to class. The representative rectangle is the next point on here. One rectangle can be represented clearly if I think of the top minus the bottom as a rectangle here. The height would be the top minus the bottom, and the base would be which axis? The x-axis. So I'll have a delta x as my width of my rectangle. That height we talked about as top minus bottom. So what's the height here? Well, the height here, top would be negative x squared plus 4. And I'm using parentheses because we might have to distribute eventually. That would be our height, top minus bottom. We can set up the integral, and if we set up the integral to express this area, the limit of the sum, oh, that's just an integral. A sum of all of the rectangles between the two curves. And so that rectangle right there is base times height, or height times base. So I have negative x squared plus 4 minus x squared is my height times my base. Well, there's another reason why we use the dx. It represents a product from the left-hand side to the right-hand side. Now this, here we say we're just going to use the calculator to evaluate this integral. So let's go over to the calculator for a second, and we're going to type that integral into the calculator. Be careful though, because before I do, I want to remember the calculator is going to force me to put another set of parentheses in. So I want to write that down on my paper and then go and type it straight into the calculator. So here we go. Let's try that out. function curve, I am not going to actually put it into y equals. Instead, I'm going to remain on the main screen and just use my alpha function or alpha window. And remember that f and int is going to give me the integral. I can type a negative root 2 in here. Square root 2 to a positive square root 2. Then inside the integrand I wanted, you can certainly over parentheses, but I'm going to note that I don't need any of those parentheses. Negative x squared plus 4 minus x squared. Don't bother adding those. Let the calculator do it. And then this little d blank is dx. Okay, let me say go. All right, so that's your answer. Remember again, if this was by hand, I'd have to go through all of the steps to turn that into an antiderivative and then evaluate it on the 2 points. But we're just going to use the calculator as an example here. So 7.542 is the area. So this equals 7.542. There we go. That would be the area that represents not just that one rectangle I drew, but the region contained between the two curves. Okay, let's try another one. This one I've set it up a little bit more for you just to get cut to the chase. We have a parabola elevated by 2, that's the x squared plus 2, and then we have y equals negative x, line going downwards through the origin. They provide me with an interval this time on the interval 0 to 1. So I'm going to use my brain to sketch that like we did here, but then I'm also going to designate the left and the right sides so I get an idea of where that area that I'm finding is going to be. Remember again, 99% of the time functions like these, we assume you know which one is higher than the other because they're two very clearly easy to graph functions. But if you note that I don't need the graph to see that the function that's on top is this parabola up 2. So this represents my top, and then the y equals negative x represents my bottom. Remember, we're always integrating from top to bottom.
Thank you so much. You guys do too.
Oh, there's Mrs. Sigmund. And so you see below in the integral, we have the top minus the bottom. Be careful here because that's noting the double negative, top minus negative x. And so as I showed you earlier, don't forget you're doing some subtraction and we might have to distribute that, especially if we did this one by hand. So we got a double negative there. And then the boundaries that they give me are from 0 to 1. And so I see those on my integral. Oh, well, you know what? Let's just do this one by hand. So what do we do? Okay, so we have an integral. I'm going to get rid of some of those parentheses and make it a little bit cleaner looking. And put this into descending order, because I like it that way. Fairly simple to integrate this polynomial. X cubed over 3 plus x squared over 2 plus 2x from 0 to 1. So now we need to evaluate. Plug in first the 1. So 1 cubed over 3 plus 1 squared over 2 plus 2 times 1. Then I note that everywhere that I plug in the 0, I'm going to get a 0, so I'm subtracting nothing essentially. And then simplifying this, I see a common denominator of 6. So I got 2 sixths, 3 sixths, and 12 sixths. So we have a total of 18 sixths or 3. So let's double check. I really encourage you to use your calculator a lot during this section so that we can get much better at using calculators for integrals. It's one of those things on the AP test that up until now we've neglected it. So I want to encourage you in this unit to use that calculator. Let's type it in just to double check. Okay, so I gotta get my little, oh my gosh, what am I doing? Okay, did we get my integral function, integral infinite? We have from 0 to 1, x squared to minus, just because I can, negative x. So there's my top minus my bottom, dx. Oh, they gave me a syntax error. This is really helpful. If you've typed something in wrong, it'll tell you it can't do the problem. So let's go to, this is a good example of what to do when you get an error. Go to the go to and hit enter. Oh, it notes right there with the flashing cursor what I've done wrong. Now, I don't know if you notice or not, that's a minus sign, not a negative. So I have to go and replace it with a negative x. Let's try it again. 2.83. I did something wrong. So this is giving me an idea of, oh, my math's wrong. Math. Enter, enter. That should be 17/6. I added wrong. Let's go back. Figure that out. I got 18/6. Oh, the 12 plus 3 is 15. 16, 17. 17. 6. Look at that. Get your problems right away. All right, so there's our answer, 17/6. Remember, I don't know how many of you do remember, this is a good learning moment for me and you. I don't know if you remember or not, but when we talk about using the calculator on a calculator problem, you would go right from the integral step and the answer, and that's all you would need to include. No steps in between. If you're on a calculator part of the test, do not integrate by hand. Use the calculator. It will be correct. However, if we're on a non-calculator test question, and we do all this work, and then I add it incorrectly, I'd lose my point. So my suggestion has been, and I know a lot of you don't like it, stop at one of these two steps prior. You don't have to come down to the 17/6 unless it's multiple choice. You can stop as long as you have evaluated.
Miss Ellis, to the main office, please. Miss Ellis, to the main office.
Okay? So stop at an evaluate step if you're on a free response question, especially if you're short on time. Okay, so let's move on. Next problem is a trig problem. Very often, we want to test you not only on your knowledge of derivatives and integrals, but also what sine and cosine look like and how they act and when and where they're equal to each other on the xy axis. So the first question is, do you know what the points of intersection are on these two graphs? And remember before, on the previous problem, I found the points of intersection by thinking or solving for where the two functions are equal to each other. Now, if you think about your unit circle, we know that happens at pi/4, and it also happens down here in the other quadrant. And if we think about that value on the unit circle, here's pi, so this is 5pi/4. So those are going to be my 2 points of intersection. This graph does not show it to you, and if you were to use a calculator, it's not going to give you a radian value if you use the intersect function on your calculator. We need to know these trig values and the angles. So we've got our 2 points of intersection, pi/4 and 5pi/4. I also have the graph here. We can see now also clearly which function is on top and which is on bottom, and also the region that the two curves create for their intersection. So I have a rectangle on there, and the rectangle is going to be the length of the rectangle. So the length of the rectangle in this case is the base. I'm seeing it's also a delta x, or a little bit of x. But what's the height of that rectangle? This value here. Remember again, top minus bottom. The height is, on the top I have sine x, and on the bottom I have cosine x. So there's my height. Here's my length or base. The variable of the integrand, notice both of those that I just calculated above are in the variable of x. And the boundaries, pi/4 and 5pi/4, are in the variable of x. So everything goes together. Set up the integral and find the antiderivative. Okay, so I'm going to go back up here again. And in this space here, we're going to integrate. So the area is equal to the integral from pi over 4 to 5 pi over 4 of sine x minus cosine x dx. That's, remember, top minus bottom. Integrate by hand, we can do this. Sine x integrates to negative cosine x minus the integral of cosine x is sine x. We want to evaluate this from pi over 4 to 5 pi over 4. All right, so we're going to have a lot of parentheses here. We're going to need to know the cosine and sine values of our radian values given, and we're also going to have negatives and lots of them. But I note that cosine x and sine x are both the same at 5 pi over 4, so as I'm plugging in the top boundary first, I'm going to have negative root 2 over 2 minus root 2 over 2. And then as I plug in the bottom boundary, I'm going to have a pi over 4, cosine of pi over 4 is also root 2 over 2. So I'll have, again, and I'm not going to use the top minus bottom yet, I'm going to do that in blue. Actually, here, I'm going to do it like this. Here's the top plugged in, and here's the bottom plugged in. So let's go back over and plug in pi over 4. Cosine pi over 4 is negative root 2 over 2. And minus sine of pi over 4, root 2 over 2. Huh, curious. I think I did something wrong here. Okay, let me go back to that very first thing in the red. Plugging in sine pi over 4, remember down here, both the cosine value and the sine value are negative, so this is actually doubling my negative here. Okay, that makes a little more sense. So I don't know if I can sum this up. There's so many little things going on. The two red values, when added together, give me a root 2. And then I have the two black values, when added together, give me a negative root 2. And the double negative gives me a plus. So my solution looks like 2 root 2. Check it on the calculator. So we're going to do that. Let's go ahead and run over the calculator. I'm going to get a decimal value. Hopefully, I'm right. I don't know if anyone can tell, though. I think I'm wrong already by looking at this area. Now, before I touch the calculator, recall that we talked about area as being positive or negative. And it looks like the area up here that I'm sketching on looks positive. And then it looks like the area down here looks like it's negative. So it almost looks as if the black and the red cancel each other out. And I'm thinking, oh, well, there should be no area because the black is positive and the red is negative. But the difference between the earlier units and now and accumulating positive and negative areas is that we have called this area space, square footage. And this is the type of area that actually is more of a total area idea. I have actually made a region on the graph, and I'm calculating the square footage of that region, which should all be positive. This is a magnitude, not a positive or negative. So let's double check what the calculator says and see if it confirms what we think. So we're going to put in our integral, and I have, on the bottom of my integral, I have a pi over 4. And on the top of my integral, I have a 5 pi over 4. The integrand is top minus bottom. So we have sine x. Got to close that parenthesis on the argument. Minus cosine x dx. And hit go. That's a negative. But I was in geometry. You might have been in physics. Let's try it again. 2.828. Now, I had as an answer 2 square roots of 2, and I'm going to validate that, yes, they are the same value. So we have the 2 root 2 is equal to, or approximately equal to on the calculator, 2.828. Now in red here I have the answer that you would get if you had just gone straight from the problem to the answer on a calculator section, whereas the other one is the exact answer that we would get by adding and subtracting after we integrate. All right, lots of math going on here, not just calculus. Okay, the next example gives us the idea that if you have two curves that go back and forth, notice one is a degree 3 and the other is a degree 2, so they have varying behaviors. We actually have more than 2 points that intersect. And here I see that there's a first intersection at -2, 8, a second intersection at 0, 0, and a third intersection at 2, 0. So I have 3 x values where we intersect these two curves, and it creates this bubbly region, and you see that I've drawn in some rectangles already to represent the heights and the bases of the areas that I'm going to accumulate. So if we have functions that go back and forth like this, we actually have differing tops. This is the cubic function. Let's call this one y1. So at first, y1 is on the top, but then later after the origin, y1 ends up being on the bottom. And the other function, let's call it y2, this negative parabola, in that first region we have that being on the bottom, and then it exchanges and it becomes on the top. So in order to set up this integral, we have to think of it as 2 different spaces, 2 different regions. And we will have to use those intersection points to combine those 2 regions, and we're just going to add those 2 regions together. So let's see what it looks like. Again, we have the functions, we have the sketched graph, and if you note, the top function that I was claiming to be y1 is seen right here, minus the bottom function, which I called y2, which is here. So we have top minus bottom again, always, 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 top function minus bottom function. And on the interval of -2 to 0, which are the points that enclose that curve. -2 is the beginning and 0 is the end. So we see that on the definite integral. And then we add that to the other area where you see that the functions have changed place. Now we have the parabola as the top function and the cubic on the bottom, top minus bottom. Lots of math on that one. Not going to really do it right now. I highly encourage you to practice integration, to do this by hand, and then maybe even type it on the calculator to confirm. But we would have to do all that work, step by step, being careful. I'd probably suggest maybe rewriting this integral if you are going to do it by hand, remembering you have a distributive. Nope, sorry. So we might want to combine our terms and write it as one integral rather of descending polynomials rather than, oh look, my x squares go away, rather than having all those little pieces and parts. That's not a plus, 2x, that would be a minus 2x. And so there's the simplified polynomial for the first one, and then by hand, the second one, I have a -3x cubed, again x squares cancel each other out, plus 12x. Oh look, wait up there. That could have been minus 12x. Yeah, so we have some different things. So, I mean, be careful. The more you can do if you're going to do this by hand to simplify, the better off you're going to be. Okay, so I'm just going to move on. I don't want to integrate this one. I want to get on to some other things. When we take the next example, I've graphed it for you. And I've graphed it for you with actually the first one that I'm graphing in number 5, or in example 5 now, has a line, y equals x minus 1, but then it has a sideways parabola, x equals 3 minus y squared. And so that's the sideways left-facing parabola you see that is 3 units to the right. Now, in this problem, I have differing tops and bottoms, as you can see by the graph. But if you look at that right blue triangle on the screen, its top and its bottom are the same exact function. So it's not quite easy to set up an integral of top minus bottom in this case. So we have some different ways to look at this function. Instead of using a dx, or everything in the integral in terms of x, we might want to flip it. So in our boundaries, talk about multiple defining functions. Now what I mean by that, you see, I have one function on the top, and then on the bottom, and then I have one function and itself on the bottom. Lots of odd boundaries in this. We don't necessarily want to do this the same way. I could divide the region up into subregions as defined by this little dashed line here. Calculate the left region with a top minus bottom. Maybe calculate the right region by doubling this shape, which would be 3 minus y squared to 0, and then adding on the bottom area. That's kind of difficult, so let's go to a different method. We could flip our heads sideways, and instead of drawing our rectangles up and down, we could draw them back and forth. So you note that if we use these vertical rectangles, we need to have our functions not in terms of what we usually have, which is y equals f of x, but instead we're going to flip them around and solve for x equals. So we're using x in the integrand. X equals functions of y. And we're going to have equations of the variable y. And we're going to think of, instead of top minus bottom, we're going to think of the top being actually on the right side, and the bottom being on the left. So we have a flipped version of our integrals. So that's what this speaks of. This speaks of the integrand being in terms of y. All of the stuff inside the integral are y values. Not only the integral itself inside has a bunch of y's and dy, but also these intersection points here are no longer going to be x values. Instead, we're going to be using the y values to determine the beginning and the ending of an integral on the y-axis. So let's see how this one is set up. We have our two curves, now both solved for x. Notice that all I did with the line is flip it around and say x equals. So I have two different functions that are both in terms of y here. And perhaps I should say, with some colors, the top function is the 3 minus y squared. And I'm not going to call it the top. Okay, top minus bottom, or right minus left. We basically have more minus less either way. And then the other function is this line, also in terms of y. So we're going to make the length in terms of y instead of the height. So the variable of y is inside the integrand. So we talk about top minus bottom with x heights. We're going to talk about right minus left with y heights. So the integral will look like this. Note I talked about the intersections of these points, and you see on the integral, we start out at a y value of -2, not 0. So this is, or not 0, 1. This is -1, -2. But the value that we want to use on our integrand is, since we have y values here, we need to use the y value for the ordered pair of that intersection. The other intersection being way over here is an ordered pair of 2, 1, but we want to use the y values. And so we have both y values inside the integrand as well as on the definite integral itself. Now, how would you solve that integral? Well, you have some different options. Clearly, I could do it by hand again, and I don't really care what the letter is. I'm solving an integral with antiderivatives. I could do that by hand. It's clearly easy. It's polynomials. Get y, negative y cubed over 3 minus y squared over 2 plus 2y, and then plug in our bounds. Or I could use my calculator, and I can go ahead and just use the main screen on the calculator and do that. Now it says y, but it doesn't matter. If I can use my calculator correctly with the integral that I have written out, all I have to do is type this in and make sure I type in the same letter of the variable every time I see a y. I'm going to type in an x. Now this is not going to give you the graphical representation that we see above, but it will give you the numerical value that's equivalent. Go ahead, try it by hand, validate it on the calculator by plugging in x's instead of y's. And it's just a variable of integration as long as we can get that to match. And it will on the calculator come out with the same value of that area between those two curves. Here's the way of setting up the integral if we used dx and the green rectangles that you see. We have to solve the function, the parabola function for y equals, and you see that we have a plus or minus. Don't forget, you square root both sides, you get a plus or minus. That's going to give us the top branch of the parabola as well as the bottom branch, but in two separate functions. In order to set this up, whoa, there's lots of things going on. The first integral describes the first region that we see between -1 and 2, and the top function being the line, the bottom function being the parabola. Why does it say plus though? We usually don't use top minus bottom. So here's the top, and here's the bottom. So this is actually minus the bottom branch of the parabola. And that's what you see, why you see that plus there. Clearly, an error that many of us might make in setting it up by doing it this way. And then we see that the addition of the second region, this parabola upon itself, is really taking top. Now the top is the positive branch of the parabola minus the negative bottom branch of the parabola. So we see that plus again there. I also said that you could see it with some symmetry, and if I just took the region from the top to 0 and doubled it, this represents also 2 times the region that I have sketched in, shaded in black. Now, clear as daylight, I don't want to integrate that one. Much easier to integrate the previous example with the y values. I don't want to integrate these if I don't have to. Way too much going on. I don't want to have to try to figure out all these subregions. So if you can tip your head sideways and see a top and a bottom, tip your rectangle sideways. Okay, we might have some geometry. So we're flipping over now. We're on example 6. When we go to example 6, we see a square root of x curve on the interval of 0 to 4. So graphically, that looks like this. And we have the area under the curve from 0 to 4. So I can use some geometry there. And I see a triangle. Now the problem might actually be find the area from 0 to 4 underneath the radical. And that would be this region, which is not that hard to set up. We've done this before, actually. From 0 to 4 under the area, or under the radical x dx. Well, that just defines us down to 0. Now, notice again, I have top minus bottom, though. We've created this new idea of top minus bottom as an area. But the bottom in this function bottoms out on the x-axis. So minus 0, we just don't see it in our normal idea of integrating area under a curve. But what if we change that into just slightly different to find the area of the shaded triangle and subtract it? I have no idea what this problem is doing. I'm trying to figure it out as I'm talking to you. Huh. So what region does this calculate? Looks like the region that's calculated here is that blue that I sketched before, from 0 to 4, minus the shaded region of the triangle, would give me perhaps this region. I don't know how that would be phrased. That's okay. We might see this in the future. But we might need to use some geometry to quickly subtract out a given area. Okay, that problem's not so great. On your paper, for the rest of the problems that you see, 7, 8, and 9, I encourage you to try them out. We'll talk about them when we get back to school. You do also have, to go along with this, I've provided you with a sheet to download, and it looks like this. Doesn't say pop quiz though. But I want you to use the areas that we've described here and use the functions that I've given, f and g, to just write an integral that would represent the shaded region. And so there's a lot of different varying kinds on there. By the way, this one is a lot like that last problem, where I have to find a region with an oddly erased piece. I've also provided with this worksheet some examples of sideways rectangles. I encourage you to draw in a rectangle every time, just so you can see where the width is, whether it's a dx width or a dy width. All right, so we'll have this to review as soon as we get back from spring break. Okay, so this is the end of section 7.1. Hope you enjoyed yourself. I'm going to do a second recording for 7.2, a bit more interesting. Hopefully you've enjoyed it.